This is part 4 of section 3.3. Another common application for logarithms is when we're talking about half-lives. The half-life of any quantity whose value decreases with time is the time required for the quantity to decay to half of its initial value. We often use this when we're talking about radioactive elements. They also talk about it in the medical field for how long it takes for half of a medicine to be removed from your body, that kind of stuff. Okay? And obviously, every individual thing is going to have its own particular half-life. So there is a constant involved that is particular to whatever it is you're talking about. Half-life formula. The half-life H of a substance undergoing exponential decay at rate K, that's going to be dependent on whatever it is we're talking about, is given by this formula. H is equal to negative natural log of 2 over K. Okay, so what we're often going to have to do is we're going to have to find K first. We're going to be given enough information to find it, and then we're going to be asked to use it often, okay? In an experiment, 100 grams of the radioactive element strontium-90 decayed to 66 grams in 15 years. Find its half-life to the nearest year. Okay? Now this is exponential decay. And I can use this, A of t, sorry, to find a K value. Okay? So the amount that we ended up with was 66. We started off with 100 in 15 years. Okay, now I'm going to divide both sides by 100. You get 66 over 100, which is 33 over 50, equals e to the 15k. Now convert this to logarithmic form. So the e comes over here, and remember log base e is natural log. So I have natural log of 33 over 50 equals 15k. So my k value is natural log of 33 over 50 divided by 15. And since this is exact, I'm going to leave it like this for the rest of my calculations in this case. All right? So H is negative natural log of 2. And I'm just going to write this as divided by K and do all of this. Because it's easier than dealing with a complex fraction. Okay, so if you plug this into your calculator, you will find that H is approximately 25.022. And then they ask us to round to the nearest year. So its half-life is approximately 25 years. Okay. And then one of the most common uses for logarithms is radiocarbon dating. Ordinary carbon, which is called carbon-12, is stable and does not decay. But carbon-14 is a form of carbon that decays radioactively with a half-life of 5,700 years. The age of an item that contains organic material can be calculated by determining how much carbon-14 has decayed. Okay? Because after something dies, an organic something dies, it no longer absorbs carbon-14. So the amount that we have in our bodies when we die is what we have. We don't ever gain any more, but it will start decaying. Okay? So let's look at this last problem. In 1960, a group of scientists from the British Museum of London investigated whether a piece of art containing organic material found in Tutankhamun's tomb had been made during his reign, or as some historians claimed, whether it belonged to an earlier period. We know that King Tut died in 1346 BCE and ruled Egypt for 10 years. What percent of the amount of carbon-14 originally contained in the object should be present in 1960 if the object was made 194 years before King Tut's death? Okay, now, so I'm bringing this over from the previous page. The half-life is 5,700 years. Because that's the half-life of carbon-14. Okay, now we want to find K value, and I can use the half-life formula for that. The half-life formula is H is equal to negative natural log of 2 over K. I can just plug this in, so it'd be 5,700 is equal to negative natural log of 2 over K. Okay, so just solve this for K, and you get that K is equal to negative natural log of 2 over 5,700. And with radiocarbon dating problems, we generally do use an approximation for this. And plug it in, and you get negative 0.00011216. Okay, now we have, going to our radioactive decay model, the amount that we should have at time t would be the initial amount, e to the negative, to k, which is a negative number, so it is a decay problem, times t. Okay. So we know we need to figure out what t should be. Okay, so figure out how long ago we're looking for. In 1960, except I can't write, 1960, and this is BCE, so I need to add 1346. So that would give me how many years ago he died, but we also want it to be 194 years before that, so I add another 194. So I'm wanting this thing to be 3,500 years old. Okay, so I'm going to plug this in. A of 3,500 is equal to A naught times e to the negative 0.00011216 times 3,500, which is A naught times e to the negative 0.4256. Now, it may be bothering you that we don't know what A naught is, but that actually doesn't matter because we're trying to figure out the percentage of our original that we have left. So it doesn't really matter what the initial point is. We're looking for the percent. So get a decimal approximation for this. And you get this. Okay? Now this is the percent we're looking for, but written as a decimal. So what is this as a percent? Multiply by 100, and 65.34%. We would expect that object to retain 65.34% of its original carbon-14 levels.